Okay, so today we are going to derive the equation for work associated with a polytropic process for a system where the volume is changing, and B, a control volume system. So to start out, we're just going to write out our definitions of work and the polytropic process. So we're going to start with work equals the integral of P dV, because we know for a system where the volume is changing, we want to have our variable be the volume dV, because we know volume is changing and pressure changes as a function of volume. So to get our pressure function, then we're going to say that PV raised to the n is equal to a constant C. This is just the standard polytropic process equation. Next, we solve for the pressure as a function of volume so that we can plug it into our integral. It's very simple. It's just P equals C times volume raised to the negative n, which is the same as C divided by volume to the n. Now we substitute in to our work equation. We get work is the integral of pressure, which is CV raised to the minus n dV. And then we're going to evaluate this from just standard from V1 to V2. Our next step is just simple integration. We know that in the power rule, work now is equal to C times V raised to the 1 minus n, because we're going to increase our exponent by 1, and then we're going to divide the entire quantity by that exponent. And this is still evaluated to V2. Next step is to plug in our values. So we end up with CV raised to the, this should be C times V2 raised to the 1 minus n minus C times V1 raised to the 1 minus n, and then this whole expression divided by 1 minus n. Next, we know that for a polytropic process, the pressure and volume at any point along the process are equal to the same constant. So we can say that C equals P1 V1 the n, which is also equal to P2 V2 to the n. Plugging in these constants, P2 V2, and then P1 V1 to the n is going in for the second C, P1 V1. And this is all still divided by 1 minus n. And there is our equation for the work, should have work equals here, the work for a system where the volume is changing. For n is greater than 1, P2 will always be less than P1, and V2 will always be greater than V1, which means that our gas is expanding, and that implies that we have a positive work because we're getting energy out of our system. All right, now moving on to part B for a control volume system. We know here that the only thing that's really changing is that we're switching our PdV into a negative, so the negative integral of V dP. And we're going to keep the same polytropic process equation, PV to the n. C. Our next step is to solve for volume, which is equal to the quantity C divided by P raised to the 1 over n. This equation we then plug into our work equation. So we get the minus the integral of C over P to the 1 over n dP evaluated from P1 to P2. Next up, we just have our fairly simple integration. Once again, I'm going to rewrite this as minus the integral of c times, or c to the 1 over n times p to the 1 over, or to, sorry, p to the minus 1 n, because it's in the denominator, bp. And this integral works out to, we have, I'm going to put my parentheses, c to the 1 over n times p to the 1 minus 1 over n, all divided by 1 minus 1 over n. Now plugging in our p1 and p2, we find that work equals c to the 1 over n times p2 to the 1 minus 1 over n minus c. These should both have negatives in them, by the way. There we go. Minus c to the 1 over n times p1 to the 1 minus 1 over n, and then this whole expression divided by 1 minus 1 over n, which I'm actually going to rewrite here as n minus 1 over n. And once again, knowing the values for our constant term here, we can plug them into our work equation, and I'm going to incorporate the negative sign as well as move the denominator to the numerator and flip it over. So we have n over n minus 1 times the quantity. C at pressure at point 1 is going to be P1 V1 raised to the 1 over n. See in there. And then we are going to multiply that by P1 to the 1 minus 1 over n. Now we can subtract P2 V2, which is the constant at point 2, raised to the 1 over m times P2 to the 1 minus 1 over n. This simplifies down quite nicely, thank goodness, it's kind of a mess. N over n minus 1 times P1 V1 minus P2 V2. And that is our expression for the work in a control volume system. And I've now realized that I left off the V1 and V2 are supposed to be raised to the n in these constant expressions. For n is greater than 1, the pressure at point 2 will always be less than the pressure at point 1, and V2 will always be greater than V1. This means that we'll have positive work because the quantity n minus 1 in the denominator will always be greater than 0, and P1 V1 minus P2 V2 will always be greater than 0 because we are expanding our gas.